Hi everyone, this is the 17th lecture in the series Mathematical Methods for Economics. The topic for today's lecture is limits. Now in the series so far we have covered mathematical preliminaries and we have talked about various types of functions which were actually a build-up to facilitate the discussion of what is to come now. So now we're going to change track a little bit for what is known as differential calculus, which is a subfield of calculus. Calculus basically is the mathematics of change, and the central idea in differential calculus is the rate at which a function changes. Specifically, we examine how changes in one variable relate to changes in another. In fact, if you are familiar with the concept of the derivative, you would associate this with the instantaneous rate of change that we will take up in a later lecture. So you might ask, why should we study calculus as students of economics? What are the applications of calculus? So if we look at the applications, actually calculus has a whole variety of applications, including those in economics. And we might, for instance, want to use calculus, for example, to examine the rate at which an economy grows over a period of time, or the rate at which a disease spreads, or how a change in interest rate affects investment, and so on and so forth. But let me not digress too much. Let us first discuss limits, because that is the topic for today. And limits, in fact, they form the building block, the fundamental tool for the study of calculus. So let's get started. So Anton, the author of the book Calculus, he writes in his book, and I quote, "The fundamental building block on which rates of change rest is the concept of a limit, an idea that is so important that all other calculus concepts are now based on it," unquote. Basically, we are trying to convey here that limits are the basic building block, the fundamental building block for the study of calculus. So please pay attention. This is the base that you must be strong about when you go ahead in your studies. Now, the concept of a limit is basically, let's understand what we mean by a limit. The concept as such is basically, it is the idea of approaching. It is the concept of a limit is concerned with the idea of approaching or coming close, but not actually attaining the value. So let me give you, before I do the formal mathematics, let me first walk you through a couple of visuals and give you an intuitive sense of what this concept of limit is all about, what we mean by approaching or coming close. And let's see how that works out. So if you look at the visual here, this is the graph of the function x squared minus 2x plus 3, right? As you can see here, the value of the function at x equal to 3 here is 6. But actually, we may not be interested as such in the value of the function at x equal to 3, and we may want to understand the behavior of how the function behaves as x comes closer and closer to 3. So as x approaches 3, we want to understand how this function behaves. Okay, so we can do this in this way. If you look at this video here, basically we can approach x equal to 3 from values less than 3 or from values greater than 3, right? And we can slide along this graph. You can see the pointer here. As we slide along this graph, you can see the values that we traverse. So if we start with, let's say, the value 2.9. At 2.9, the value is 5.61. At 2.97, the value is 5.881. And this way, we can move closer and closer towards x equal to 3, right? And you can see the value converges to 6. Similarly, we can take values of x larger than 3 and see how the function changes value, right? So let's slide across the graph. and here we have the value 3.2, where the value of the function is 6.84. As we come closer, the value, let's say at x equal to 3.15, the function value is 6.622. It's decreasing. Then at slowly, if we come towards 3, so if we come to 3.05, for example, the value of the function is 6.202, and again you can see the value is steadily converging to 6, right? So this is the idea of coming closer and closer to x equal to 3. We see how the value of the function changes. I also have this table here in case you did not follow the values that I took for x. So these were the x values, and you can see basically I am approaching x equal to 3 either from values less than 3, 2.89, 2.9, 2.97, or from values of x larger than 3. So 3.2 moving to 3.15, then 3.05, and here you can see whether we move from the left or from the right, the convergence is towards 6. So on the left we moved, the function value changed from 5.57 to 5.61, it was increasing, then 5.88, and then gradually moving towards 6. From the right, the value was at 3.2 was 6.87, then reduced to 6.2, then 6.2 at 3.05, and again the convergence was towards the value 6. So here we then write, this is how we write things mathematically, that the function x squared minus 2x plus 3 approaches 6 as x approaches 3. We can also alternatively state this as x squared minus 2x plus 3 tends to 6 as x tends to 3. Or more formally, we can say that the limit of the function x squared minus 2x plus 3 as x approaches 3 from either side is equal to 6. Okay, so the limiting value of the function x squared minus 2x plus 3 as x approaches 3 is 6. Okay, now here is another example. So if we just go back to the previous example, here the situation was one where the function was defined at x equal to 3, right? And what we are trying to convey here is that the function may be defined, but we are not interested in the value of the function at x equal to 3. We want to understand the behavior of the function around x equal to 3. And in that sense, it doesn't matter whether the function is defined at x equal to 3 or not defined at x equal to 3. So here, this example that I have on the next slide, it actually is, giving a different flavor to the things here, which is to say that here you have a function which is x squared minus 25 divided by x minus 5, which you can see is actually not defined for x equal to 5. So here there's a slight twist to the problem. In the first example, the function was defined at the point of interest. Now here the function is not defined for x equal to 5. What do you see here? If x is equal to 5, the numerator becomes 25 minus 25, which is 0. The denominator becomes 0. So basically the fraction collapses to 0 by 0, right, which is not defined. So the point here is, okay, we don't know what the value, the function is not defined at x equal to 5, but can we still ask the question, what happens to the function as x comes closer and closer to 5? Right? That is the idea of a limit. We can ask the question, what happens to the function as x comes closer and closer to 5. Now I'll show you a visual here, which is actually the graph of this function. I'll explain in the second part of the lecture how this graph comes about. But basically you can see here that I have shown the visual here for the function x squared minus 25 divided by x minus 5 for all non-negative values of x, and you can see here that the function is not defined at x equal to 5, right? You have this hole in the graph here to suggest that 5, 10, this point does not, it's not part of the graph of the function. Okay, so never mind. The point here is, can we understand the behavior of this function as we approach 5? Now we can again approach 5 either from values of x less than 5 or from values of x greater than 5, right? Either way we can approach this number x equal to 5. And again we can slide along this graph. Let's see how the values change. So again let's look at a couple of values. Here we have 4.8 where the value of the function is 9.8. And let's move a little closer. As we move a little closer to x equal to 5, you can see the value changes to 9.8 at x equal to 4.8. Again you can see the value is converging to 10, right? We are moving closer and closer to 10, and then we reach that hole where the function is undefined. Similarly, we can just slide along the graph from values of x larger than 5, and here again I've shown you some values here. So at 5.4 the function takes on the value 10.4. As we move closer to x equal to 5 from the right, you can see that the value drops to 10.3 at 5.3. Then as we move closer and yet a little closer, so you can see at 5.1, 5.16, yeah, you have 5.1 here where the value of the function is 10.1. So you can see here again there is this steady convergence, right? So the function is not defined at x equal to 5, but if we take values of x to the left of 5 or to the right of 5, the function converges to the value 10, and in that sense we are talking of a limit here. Okay, so let's see how we're going to write this. So what we have seen here is that x squared minus 25 divided by x minus 5 approaches 10, the number 10, as x approaches 5. Or more formally, the limiting value of x squared minus 25 divided by x minus 5 as x tends to 5 is equal to 10. So we have different ways of expressing ourselves. We can say x tends to 5, or we can say that x approaches 5, or we can say x comes closer and closer to 5. So whichever way you're comfortable expressing yourself, that is absolutely all right. So basically this was the idea of a limit. Now let's take a look at a very preliminary definition to just kind of capture what we have just discussed in a slightly more formal way. But we will look at the precise mathematical definition in the next video perhaps, and we'll also look at, in a bit, we'll also look at the rules for computing limits. But let's first set up a preliminary definition for understanding the concept of a limit. So let us suppose we have a function f which is defined for all values of x near this point a, but not necessarily at a. So as I just said, so in the first example where we were interested in the behavior of the function around x equal to 3, there the function was defined. But in the second example, the function was not defined at x equal to 5. So that was our a. A in the first example was 3, a in the second example was 5. So the function may be defined for x equal to a, it may not be defined, but it is defined for all x near a, right? And if we have a situation where the function f of x tends to the number L, a finite number L, as x tends to a, then we write that the limit of the function as x tends to a is this number L. Okay, the limiting value is L. Note here that L has to be a finite number. It is a fixed numerical number. And also what we are talking about here is a two-sided limit, because we have to take into consideration here values of x from both sides of a here, as we did in the first two examples. Okay, let's formalize things a little bit more. Right, so when we write the limit of the function f of x as x tends to a is L, it basically means that I can make the function f of x as close to L as I want for all x sufficiently close to a. Now, this may not make much sense at the moment, but once we set up the precise mathematical definition of limits, this will we'll be able to convey this statement in a more proper manner. So, but note here that when I say we can make the function come as close to L as we want for all x sufficiently close to a, Note here that first of all, we must take into consideration values of x on both sides of a, which is to convey that we are taking a two-sided limit. And also the point here is that we're not interested here in the value of the function at a, right? The function may or may not be defined at a. We are interested in how the function behaves for x values close to a. So I'm repeating this again and again because I would like you to really internalize this aspect. Now also I said that this number L has to be a finite number, right? So the point here is that if the function f does not tend to any fixed number, a fixed numerical number, as x tends to a, we say that the limit does not exist. Okay, so it has to be a finite real number, and if it does not tend to any fixed number as x tends to a, if the function does not tend to any fixed number, we say that the limit does not exist, or the function does not have a limit as x tends to a. So what I'll do is I'll walk you through three cases to show different situations where the limits may not exist, limits do not exist. Okay, so let's look at case 1 where the limit does not exist. You can see here that as x approaches a from either side, the function is just shooting off to infinity, right? Infinity is not a real number, right? The function becomes infinitely large as x tends to a from either side. So we write here that the limit of f of x as x tends to a is equal to infinity, but this is the case where we say that the limit does not exist. Okay. Also, as a side, though this will be covered in more detail in the next video, the next lecture, this straight line x equal to a, this is also called a vertical asymptote for the graph of f, right? Basically, the idea is when we talk of an asymptote, what does it mean for a function to approach some line asymptotically? It basically means that the distance between the graph of the function, the distance between the curve and the line which we are claiming to be the asymptote becomes smaller and smaller as we move for very large distances away from the origin. But the point here is that if we have a function that approaches infinity or minus infinity, right, as x tends to a, then that straight line x equal to a is called a vertical asymptote for the graph of f. Now this is another example that I have shown here where the limit does not exist, and this is basically to illustrate that sometimes a function might behave in such a way that you may take the limit from either side of a, but actually the limits are different. So in these cases one has to examine the one-sided limits because sometimes these come in handy, and you can see here in this picture that as x approaches a from values of x less than a, when I say x approaches a minus, that means x approaches a from values of x less than a. When I write x approaches a plus, it means x approaches a from values of a larger than a. Okay, so as you can see here in this picture, the function f of x approaches the number b as x approaches a from the left. Okay, so this b is called the left limit or the left side limit or the left hand limit, depending on which book you are reading. And similarly, you can see that this is a function where if you approach a from the right, from values of a larger than a, then from values of x larger than a, then the function approaches the number a. Right? So this is then the right side limit, the limit of f of x as x approaches a from values larger than a. This is a, okay, capital A, and this is the right limit. Okay, so let me give you an example here. Let's take the case of a step function. Right, a step function, one example that I've given you here is the graph here is one where the function takes on the value 1 if x is less than or equal to 2. I'm sorry if the axes numbers are not showing, but I think the basic idea of a step function is known to you. And the function takes on the value 3 if x is strictly greater than 2. So here you can see that as x approaches 2 from the left, the function approaches the value 1, and as x approaches 2 from the right, the function approaches 3. So the left side limit is 1 and the right side limit is 3. Now here again we have a situation where the left side limit exists, the right side limit exists, but the two are not equal, and this is a case where we say that the limit does not exist. Okay, so necessary and sufficient conditions for the limit to exist is that the left side, the two one-sided limits of the function must exist, and the left side limit must be equal to the right side limit. So first is that the left side limit and the right side limit must exist, okay, for the limit to exist, for the two-sided limit to exist, and the two should be equal. So when we say that the limit of the function is L as x tends to a, this is true if and only if the limit of the function as x tends to a from the left and the limit of the function as x tends to a from the right both are equal, and they equal L in this case. And needless to say that if one or both of the one-sided limits fail to exist, the two-sided limit will not exist. And just one more case to show where a limit may not exist. This is a situation where the graph fluctuates. You can see that the graph fluctuates between the numbers a and b. So as x tends to infinity in this case, there is no convergence. The graph does not converge to any particular value, and here also we say that the limit does not exist.